In this video lecture, I want to talk about log integration, which it kind of sounds like a separate thing, but really it's just a special case of U substitution. So I want to start with what we know from Calculus 1 about taking the derivative of natural log of a function. We know that that derivative is going to be the derivative of the function over the function, just by the chain rule. So this is something that we've done quite a bit in Calc 1. Let me just give you a specific example of that. So I want to take the derivative of natural log of something like, I don't know, x squared plus 3. Right? So the derivative of x squared plus 3 is 2x over x squared plus 3. So notice that the numerator is basically the derivative of the denominator. That's exactly what this structure tells us. So if we were to integrate 2x over x squared, x squared plus 3, right, we would recognize that the numerator is the denominator, the derivative of the denominator. So just by U substitution, we could let u equal x squared plus 3, so that du equals 2x dx, right? And so just straightforward U substitution, I would end up with the integral of 1 over u, right? Because, well, technically du over u, or 1 over u du. Du is 2x dx, which I have right here. U is x squared plus 3, so I have this, right? And that antiderivative is the natural log of the absolute value of u plus c. If I put this back in for u, which I can drop the absolute value since x squared plus 3 is always positive, that's going to give me natural log of x squared plus 3 plus this constant of integration. So similar to this, except we had this constant of integration. In this particular case, our constant of integration was 0, right? So because we had natural log of this, not plus anything. But if we had taken the derivative of natural log of x squared plus 3 plus some number, I would have still gotten this because the derivative of the constant is 0. So this is the basic idea. It's just the basic structure for log integration is I'm integrating something of the form where the numerator is the derivative of the denominator. All right. So that's really all there is to it. There's not, in terms of the theory behind it, it's just a special case of U substitution. So I'm just going to go through a few examples to see how this works. Okay, let's take a look at a fairly straightforward example to begin with. All right, we've got x squared over 9 minus 2x cubed dx. All right, so we see that the denominator, if I were to take the derivative, it would be something on the order of x squared, which is what I have up here. So that's what I'm looking for. This is 1 degree lower than this. So if I let u equal 9 minus 2x cubed, then du, after I take the derivative here, that's going to be what, negative 6x squared dx. I have an x squared dx to replace, so I have to divide out that negative 1/6, or I'm dividing out the negative 6 to get negative 1/6. So x squared dx is equal to this. So my new integral is going to look like negative 1/6 integral of 1 over u du, right? Because 9 minus 2x cubed is all replaced by u. So this is negative 1/6 natural log absolute value of u plus c, and now we just put this back in for u. Negative 1/6 natural log absolute value 9 minus 2x cubed plus c. All right, so again, pretty straightforward example. All we're looking for is a numerator that is the derivative of the denominator, or a multiple of the derivative of the denominator, because we can always divide out constants. All right, let's look at a few more examples that maybe aren't quite as straightforward as that. So example 2, I'm going to look at 3x squared plus 5x minus 2 over x plus 4 dx. All right, well, this one doesn't look like what we want at all. If anything, it looks like the denominator is the derivative of the numerator. But we can't have du in the denominator. Right? We couldn't let u equal this. Not to mention that if I took the derivative of this, I'd get 6x plus 5, which there's not really anything I can multiply 6x plus 5 by to get x plus 4. But we can't have a du in the denominator. That's a no-no. So we're going to do something that you probably have worked on in pre-calculus, which is polynomial long division. In other words, I'm going to take this 3x squared plus 5x minus 2, and I'm going to divide it by x plus 4. Right? So this combines everybody's favorite things, long division and polynomials. But it's really not that hard. It's the same idea, right? I need to figure out what I'm going to multiply x by to get 3x squared. I don't worry about the 4. The 4 is just along for the ride. I need to get rid of the 3x squared. Right? Notice this is kind of my x column. I'm multiplying x by 3x to get 3x squared. So I'm going to put this right here, 3x, and then I multiply everything. The main thing, like I said, is I want this to give me 3x squared so that when I subtract, my x squared term is gone. So I will get that, 3x squared, and then that's going to be plus 12x. Now, where students will get in trouble here is with this. What I want you to do is make sure, put it in parentheses so you remember to subtract everything, right? You're subtracting the 3x squared. You want to make sure that you're subtracting this 12x as well and that you don't accidentally add it. So that's where I think by putting it in parentheses and reminding yourself you're subtracting all of this, because 5x minus 12x, that's negative 7x. And then I bring down my minus 2. So I have to clearly multiply x by negative 7 to get negative 7x, right? So I'm going to end up with negative 7x and then minus 28, right? And again, remember, I'm subtracting this whole thing, right? So negative 7x minus negative 7x is 0, and then negative 2 minus negative 28, right? Well, that's negative 2 basically plus 28, so that's going to give me 26. So what do I do with the 26? Well, it's a remainder, right? So I can rewrite that as plus 26 over x plus 4. All right. So basically, what this whole thing right here now is equivalent to my original integrand. Right? I just basically have simplified it. So now my new integral looks like 3x minus 7 plus 26 over x plus 4 dx, this whole thing. All right, so at this point, I think the easiest thing to do is just to take these one by one, right? So the antiderivative of, well, let's do this, because this last one might be not so straightforward. So let's just say, well, the integral of, let's just break this into two integrals, 3x minus 7 dx plus the integral of 26 over x plus 4 dx. So here, the antiderivative of 3x squared, I add 1 to the exponent and divide by my new exponent, so that's going to give me 3x squared over 2 minus 7x. And now let's think about what we're going to do with this. We can bring that 26 out front, right? So I've got plus 26 integral of 1 over x plus 4 dx. Now this is a trig integral. We just let u equal x plus 4, du equals dx, because the derivative of x is 1, the derivative of 4 is 0. So this piece right here is just going to be the integral of 1 over u du, which equals the natural log of absolute value of u, which is natural log of absolute value of x plus 4. Whoops, absolute value. All right, so finally, putting it all together, we end up with 3 over 2 x squared minus 7x, and then 26 times this antiderivative plus 26 natural log absolute value of x plus 4, and then don't forget your constant of integration. All right, so again, here's just a little bit of a trick you might recognize. So if the degree of the numerator is greater than or equal to the degree of the denominator, you might try polynomial long division, giving us a new expression that we can integrate. And then this remainder term is where our log integration will come in play, because I end up with a constant over a linear term. Linear meaning just x to the first power. And we know the derivative, that's going to be a constant, so we can pull that 26 out. And the rest of this is fairly straightforward antiderivatives. Okay, so that's one special case that I wanted to discuss. Let's just look at one more example of log integration. All right, let's say we have something like 3x over x minus 6 squared dx. All right, now I could expand this out. Right, that would give me what, x squared minus 12x plus 36. Let's just take a look at what would happen there if we did that first. So 3x, so I get x squared minus 12x plus 36. So this is looking promising because we know the derivative of an x squared is going to give me an x, which is what I have in the numerator. But if I let u equal x squared minus 12x plus 36, then du is going to be 2x minus 12 dx, right? And there's not really any way to multiply this by a number to get 3x, because I had that factor of 12 there. So unfortunately, this is not going to work, even as promising as it looked. There's another way to approach this, though. We could so that's not going to work. All right, but at least wanted to kind of show you what would happen if we went that way and why. Like, I think it's important that you also understand, when have I reached a dead end? Well, when I have something here, 2x minus 12, that can't be multiplied by a number to get the numerator, I've reached a dead end. And what I want to do is maybe think about a different way to do this. So let's let u equal x minus 6. All right, then du is just dx. All right. So that's fine as far as covering. Now I've got like a u squared down here, and I have, the dx is covered with the du. But what about the 3x? How do I get that in terms of u? Well, right there, all right? Because what we can do, since this is linear, in other words, it's not squared or cubed or square root or anything like that, it's just x to the first power, I can solve for x, right? So using this same equation, I can say, well, x, if u equals x minus 6, I can add 6 to both sides, and that tells me that x equals u plus 6. All right, so let's go ahead. We'll put this in here for x, and then we'll put, we're going to put the u in here for x minus 6. So coming over here, my new integral, and actually I'm just going to take this 3 and bring it out front. I don't need constants in there. So 3 integral, in the numerator I end up with u plus 6, in the denominator I end up with u squared, and the dx is du. So now I have this. All right, well, what am I going to do with that? Well, we can simplify that a little bit. Let's write this as 3 integral of u over u squared plus 6 over u squared. All right, this is basically the idea of like a common denominator in reverse. Since these two have a common denominator, they can be combined into one term. Well, they can also be separated back into two terms with the same denominator. All right, and let's look at these separately then. So I'm going to have 3. Let's break these into 2 integrals. So I'm going to have the integral here. If I simplify, I've got 1 over u du plus 6 over u squared, which I'm going to just write as 6u to the negative 2 du. All right, well, this one, there's our log integral. That's just natural log of absolute value of u. Plus, so here I add 1 to get negative 1, then divide by negative 1. So it's going to be negative 6u to the negative 1. And remember, everything here now is multiplied by 3. All right, so let's put our x minus 6 in back for u and simplify. So I'm going to have, and we'll distribute this 3. 3 natural log absolute value of x minus 6 plus a negative is the same thing as minus. So I'm going to have minus 18, right? 3 times the 6 gives me the 18. And then u to the negative 1, that's going to be x minus 6 to the negative 1 plus c. Finally, just to simplify this one step further, usually when we think of this, we put this in the denominator, right? So I've got 3 ln absolute value x minus 6 minus 18 over x minus 6 plus c. All right, so Again, just the little trick here was to recognize that this is a linear factor, so I can let u equal that, and then solve for x in terms of u to end up with an integrand that looks like this, and then to break it into two integrals, one of which leads to a log integral. Alright, so like I said at the beginning, this is really just a special case of u substitution. I just wanted to show a few examples because there are some little tricks like this one, and then also like this this polynomial long division that then lead to a log integration scenario.